Hi, in this video we're going to discuss different approaches for object detection. Object detection is a task that combines classification of the content of image with the localization of a bounding box around it. We'll explore the evolution from anchor-based to anchor-free methods, the two families of methods that we use, and we're also going to see a taxonomy in the anchor-based models. We're going to see how we can have single-shot detectors like RetinaNet, YOLO, and two-stage detectors like faster RCNN. So object detection solves two tasks, the one of locating object with bounding boxes inside an image and classifying what this objects inside the bounding box is. So the object detection model is going to output coordinates, x, y, width, and height that frame each object, plus the class labels and the confidence scores that we have for these class labels. So this image demonstrates detection of vehicles, people, and bikes in a street scene. This could be the output that we see in a self-driving car. Each box provides spatial information saying where the things are. This is the localization part, and semantic information giving us like a label saying that inside this particular box is a person, inside this particular box there is a car. So we see that we have a regression problem computing the location of the bounding box and its dimensions is a regression problem. We're trying to estimate these coordinates, and then we're going to have a distance between the predicted bounding box and the true box, the one that we have in the ground truth dataset. We have some labels in which people have labeled where the bounding box is supposed to be, and we're going to train our model so that it puts its own labels, its own bounding box as close as possible to this one. We're also going to have another function. We're going to have the cross-entropy loss being used to tell us how good is our classification. And this is the setup that we have in most architectures. You're going to have some regression loss for the bounding box, comparing the bounding box that we are giving as prediction output with the true one that was in the labeling dataset. And then we have also the cross-entropy loss for the classification. How confident are we that what we're seeing in this particular image is a person or a bike? The network is going to output both these class probabilities and the box coordinates. Like we're going to have this probability for this being a bicycle with some number, and here we evaluate the cross-entropy loss. And then we're going to have the coordinates for the bounding box, and here we can also evaluate a loss. How off are we in these coordinates? And we can do this with any regression loss function like L1 loss, the absolute error, or we can use the Euclidean distance, the L2 loss. We can also have a parameter lambda that balances these competing objectives, like what are we going to pay more attention to, the location of the bounding box, how good it is, or the class that we're giving to the bounding box. This is something that we can balance in these equations with some lambda parameters. There are many variations on these particular loss functions implemented by different algorithms, but this is the core idea. So here we see the challenge of partitioning an image into boxes. Here we see a pedestrian crossing a street, and we see all the possible different bounding boxes and all the different aspect ratios that are able to capture where this person is. So there are two different approaches for locating people or objects on images. We can have anchor boxes, which are predefined templates that have multiple scales, or we can have some key point identification, like some direct prediction of what are the object boundaries for every query pixel. So this fundamental challenge about finding what is the best fitting anchor box, or what is the best fitting prediction for the object boundaries, is the thing that drives these different architectures and these different ways that the object detection problem has been framed. We're going to see that there is a wide variety of solutions on how to predict the best bounding box. Let's start discussing anchor boxes. So anchor boxes are like templates. We have here a template in which we have defined like 3 aspect ratios, like square bounding boxes, also rectangular bounding boxes. Some have like more width than height, and the other way around. And then we have 3 different sizes for them, like 64 times 64, 128 times 128, could be 256 times 256 when we have the 1:1 aspect ratio. And then we scale this in the different aspect ratios. That gives us this sampling grid. The image that we see on the right demonstrates how we have overlapping anchors at different scales. And each one of these anchors becomes a candidate for object detection. So after defining a small number of possible anchors and their box sizes and their aspect ratios, we're faced with a challenge, and that is that we're going to have hundreds of thousands of them in most images. So the right image here shows all candidate bounding boxes. We're going to have this class imbalance in which we're going to have too many negative examples. Like we're going to have most of the bounding boxes in the image correspond to background objects that we don't really care about. And this is going to tax the model. This is something that we need to filter out somehow, because we're going to have a computation overhead during inference. We're going to have like a lot of these negative samples being processed, and they're also going to be impacting the accuracy of our algorithms. Because if, for example, we say that there's nothing of interest on an image that has object of interests, then we're going to be getting this prediction right in most cases, which is going to make the model harder to train. So the field of object detection, when it's based on anchor boxes, splits into 2 competing architectures. We have single-shot detection, which is faster, and then we have the 2-stage detection approach, which is usually more accurate. In the 2-stage detection approach, we have first a proposal of regions, a proposal of anchor boxes that are good candidates for having a foreground object, and then we have a second stage where we finally classify these proposals. In the single-shot detector, we don't have this. We just classify all the proposals at once. So the single-shot detector is usually faster in inference, but at a cost of accuracy, whereas we have the other situation with the 2-stage detector model. The most famous of these 2-stage detector models is faster RCNN, which first has this region proposal that is basically a network that is going to classify the anchor boxes as being foreground or background, and after it has determined that something is foreground, that something has a high probability of being an object of interest, we actually crop this section from the original features that we have in the convolutional network that provides the base features. This is something that we do with something called region of interest alignment, and we finally put this into the classifier to give us the prediction, saying that this particular bounding box that is very likely to be foreground has a bike, for example. So then we have the approach in which we don't have anchor boxes. This is what the latest, at least at this point in time, the latest version of YOLO is YOLO 11. They have removed the use of anchor boxes, and instead it predicts the distance to the box edges. This has some benefits. The main benefit is that we have fewer parameters to tune. We don't need to design the anchor shapes. We don't need to think about whether it's more likely for us to see the objects as square objects or as rectangles, or if they're going to be like very close or very far away from the camera, because this is also going to affect the size of the aspect ratios. This is simpler. This is something that gives us less parameters to tune. And a key advantage that we have here is that we don't need to think about that. We don't need to think about which are the anchor shapes that are the most likely to give us good performance in our model. So this is more flexible, and so each approach has distinct trade-offs. The anchor-based approach is one that is going to be able to handle the occlusion well, and is going to be able to excel at multi-scale detection. So if you have an object that is partially covered during the run of an anchor-based model, you're going to have a high probability of catching it, because you have a template that is going to evaluate its objectness, is going to evaluate whether it corresponds to one of the classes of interest. The downside is that it's a bit more complex to tune. The anchor-free approach is simpler and has fewer hyperparameters, but it struggles with occlusion. So we need to choose whether we use one approach or the other based on the application. Then we have this model that has become quite popular in recent years that is called DETR. And this one, instead of using anchor boxes or using the grid-based approach that we saw in YOLO 11, uses something called object queries, which are some learnable embeddings. And these learnable embeddings have a maximum number. If we have 100 object queries that are learnable, that means that we're going to have at most 100 objects being detected in a particular image. So this particular architecture has shown very good performance and is relatively simple to implement. It's a combination of a convolutional base for extracting features, and then a self-attention transformer layer that is able to produce this very high quality bounding boxes. This method has become very influential and is the basis of another powerful approach called Grounding DINO. DETR is the basis of Grounding DINO. Grounding DINO is this method that is very similar to CLIP, and here grounding refers to connecting language to real-world objects, and here it's linking text descriptions to image regions. In the Grounding DINO paper, they call standard object detection closed set object detection. And this is in contrast to what they call open set or open vocabulary detection. What is an open vocabulary? When we do this zero-shot approach to say, okay, I want to have all the World Cups that appear on this particular image, even though I didn't train the model on this particular image before. I can have like a very descriptive way to say, I want to get the bounding box of the person in the center of the image that is holding the World Cup. That is something that will give us an output in Grounding DINO. And this is a very powerful approach. It doesn't perform as well as a purely fine-tuned model for a particular use case, but it's very flexible. So it allows us to curate very big data sets with less effort than having to draw most of the bounding boxes by hand. So we see that the architecture has some cross-model attention. It uses a transformer decoder to align the text and image features, and it's able to perform quite decently, even though it's trained on a dataset that is not that big, especially if we compare it to the datasets that were used to train CLIP. CLIP was trained on 400 million images, whereas Grounding DINO was only trained on 8 million images and has some very decent performance. So to wrap up this video, we saw that object detection combines classification and bounding box regression. It has different terms that get added in the loss function to solve these two problems. We use typically some variation of cross entropy loss for the classification problem, and some regression loss like L1 or L2 for the bounding box regression problem. And we also saw the variety of methods that are anchor box based. We saw the single shot detector and the two-stage detectors, and the trade-offs between them, that the models that use the two-stage approach typically have higher accuracy at a cost of computation, whereas the other ones are more commonly used for real-time performance. Like the methods that are single shot are typically having a quicker response time. We saw here also how anchor-free approaches and grounded detection work. The anchor-free approach from DETR is based on query boxes, which are learnable embeddings. And we also saw the grid-based approach from YOLO 11, which is quite flexible, even though it has this issue with occlusions. So Grounding DINO is something that has a trade-off. Like, it's usually not as accurate as a fully supervised model, but it's very flexible, and I encourage you to try playing with it in the notebook that accompanies this video.